Hey guys, this is Rick from MathX, and today we'll be doing number 12 from the AIME II of 2020. So, the AIME II of 2020, or the AOIME, has just passed. And going on YouTube, I've seen a lot of solutions for like problems like 3, 4, 5, 7, 11, 10, and I get that. Those are really cool problems. But for some reason, I haven't seen any solutions on number 12. Now, I'm not going to say number 12 was the best problem on the test, but I still had fun with it, and I think it warrants at least a solution. So, here I am, making a video showing the love for number 12. All in all, I thought this test was kind of lower than average, as there are several bashy problems with 6 and 9. But at the same time, there are also some good problems, like I particularly liked 10 and 11. But in this video, I'm just here to explain 12. So without further ado, let's just get into the solution for number 12. Let's first start by reading the question. Let m and n be odd integers greater than 1. A m by n rectangle is made up of unit squares whose squares in the top row are numbered left to right, with integers 1 through n. Those in the second row are numbered left to right with integers n plus 1 to n, and so on. Square 200 is in the top row, and square 2000 is in the bottom row. Find the number of ordered pairs m and n of odd integers greater than 1 with the property that in an m by n rectangle, the line through centers of squares 200 and 2000 intersect the interior of square 1099. So this problem has given us quite a bit of information. It tells us that m and n have to be odd integers. We have an m by n rectangle made up of unit squares, whose squares are numbered from left to right. And 200 has to be in the top row with 2000 in the bottom row. The first thing we have to do in this problem, in order to make it really easy for us to understand, is draw out this diagram, the m by n rectangle the problem speaks of. Now, we can't draw it perfectly because we don't know the dimensions, but just trying to get a rough idea of what it would look like. So here I think I've drawn a diagram that pretty much encapsulates what the problem's telling us. We have an m by n rectangle where the rectangle goes on for an undeterminate amount of time until n, and it goes down an undeterminate amount of time towards m, and we have 200 somewhere in the first row and 2000 somewhere in the final row. So using this diagram, in order to solve this problem, it'd be best to create some relationships between the numbers and the letters, as this will help make the problem easier to solve. So the first relationship that we can see is that n has to be greater than equal to 200. This is because we know on the first row it contains n elements, and 200 is somewhere on that first row. So there are two things that could either happen. 200 is before n, which means n is greater than 200, or n is 200, in which case n is equal to 200. So that's our first relationship we can derive from this. The next relationship we can derive from this is not as obvious, but still not that hard to get. We can use a relationship to derive m. Since there are m rows in this n-columned figure, each of these rows contains n elements. So after the first set of n, there's n plus 1 through 2n, and then eventually at the very last element will contain m times n. But since we know that 2000 lies in the final row of this m by n rectangle, we could say that if we take the ceiling function of when we divide 2000 by n, we can make sure that that's equivalent to m. Using some little thinking abilities, as we see that 2000 lies in the final chunk of this n by m rectangle, this 2000 must be between the product of n times m minus 1 and n times m. So if we take the ceiling function of their quotient, we should get the quotient of n times m over n, which will clearly give us m. So using this, we've established our second relationship. M is equal to the ceiling function of 2000 divided by n. Now, using these two relationships, we can deduce some possible values for m. If we plug in all the values that n could be due to this upper inequality into this lower relationship between the two, we see that m has a very specific set of values it could be. M could equal any value from the set 10 through 1. We can see that it could be 10 because if n is equal to 200 from this greater than equal inequality, then the ceiling function of 2000 divided by 200 would give us 10. But let's say we maxed n out to like some really, really large number, like 10,000. Then we'd get some really small decimal here, and getting the ceiling function of that would give us 1. And then, of course, it could be all the values in between. So we know that m could be between 10 to 1. However, it says that m and n are both odd integers. So that automatically eliminates all the even elements in this set. And it also says it's greater than 1. So we can eliminate 1 as well. So all the elements in this set that are odd and not 1 are 3, 5, 7, and 9. So we know that these are 4 possible values for m using these two relationships. Now that we have clear values for m, let's find out what some possible values of n could be. And then after we figure out all the possible values of n, we can start eliminating all the ones that don't work to find our solution to this problem. So to start, we have to start with the m equals 3 case. When m is equal to 3, 2000 divided by n ranges from 2 point something 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 all the way to 3. So the largest value of n we can obtain is 1 such that 2000 divided by n is only slightly greater than 2. Well, if n is 1000, it's exactly equal to 2. So the only way that the value of 2000 divided by n is slightly greater than 2 is if we take the number 1 less than 1000, 999. So we see that that's the upper limit to n. Well, as for the lower limit, we can just get this by dividing 2000 by 3, as that will give us a number that is approximately 3, and then taking the ceiling function of that will give us 3 once again. So doing so, we get around 666 and 667. But since it tells us in the problem we only take odd integers, we just discard 666. So we take the minimum as 667. And thus we obtain that n is in the range of 667 and 999, where n is all the odd numbers between, when m is equal to 3. If we take m is equal to 5, we see that either 2000 over n is equal to 4 point something something something, or it's equal to 5. So if we check the upper limit to see how close it can get to 4, well, 2000 divided by 500 will give us 4. So if we divide it by 500 minus 1, 499, we're going to get 4 point some really small decimal. And since we're taking the ceiling function of that, that will give us 5. So the upper limit of this would give us 499. To find the lower limit, we merely just divided once again by 5. So we do that and we get 400. However, as we did with the previous case, we have to disregard 400 because we only take odd numbers, as the problem specifies again. So we take the next smallest odd number greater than 400, which is 401. So we get that when m is equal to 5, n is between 401 to 499. Next, we take into consideration the m is equal to 7 case. So, as we've done before, to find the upper limit, we have to see how close we can get 2000 divided by n to 6 without it equaling 6. Unlike all the previous ones, if we try to divide, we won't get a clean number to 6. But we see that when we divide 2000 by 6, we'll get slightly more than 333. So, since it's slightly more to give us exactly 6, if we take slightly less, it'll give us 6 point something something something, which will eventually give us 7 because we're taking the ceiling function of that. So the upper limit of this, 333. As for determining the lower limit, we just have to do what we've done before. Divide 2000 by 7, and then take the odd number that is closest to that value. Closest but larger. Doing this, we can obtain 287. Because it'll give us a weird decimal, but just going to the closest odd number to that, which is larger than it, we obtain 287. Finally, we have to check for our m is equal to 9 case. As we've done before, to find the upper bound, we just try to get 2000 divided by n as close to 8 as possible, but slightly greater. So 2000 divided by n could give us 8 if n was equal to 250. But if n was 1 less than that, if n was 249, then it'll give us 8 point something something something, which will give us a ceiling function of 9. So the upper bound will give us 249. In order to get the lower bound, we just need to divide 2000 by 9, and then take the odd number closest to that. So when we do that, we divide 2000 by 9 and find the smallest odd number greater than equal to that. We get 223. So when m is equal to 9, n has to be between 223 to 249. Now, in order to obtain our answer, we just need to find out all the values in between these certain ranges of n that don't work. And just by adding up all these independent different cases, we'll get our n solution. So now let's do that. So now we take a look at this number, 1099. Now, this number is very special and is related to this problem, because you see that 1099 isn't really a random number. 1099 is very close to square 1100. And we see that 1100 is the median value between 200 and 2000. Because 200 plus 2000 will give us 2200, and then half of that's 1100. Now the deal with this median value means that any line through the centers of squares 200 and 2000 will always go through the center of square 1100. So if we take an idea what this diagram would look like, 1100 would be somewhere in the middle of these two squares. So if we say that 2000 somewhere over here and 200 would be somewhere over here, well then we would see that 1100 would be right about here. And if 1100 is this square, 1099 would just be 1 to the left of it. So we know that whatever line goes through 200 and 2000 will also go through the center of 1100. But whether this line that goes through 1100 also goes through 1099 depends on the slope. We see that if the slope is 1 or -1, this does not happen. But for nearly all other cases, it will happen. So From these sets we already have, we just have to eliminate all the cases where the slope will be 1 or -1. So let's calculate the slope in terms of this upper 200 and this lower 2000. Find all the ways that it could be 1 or -1. Subtract this from our total ranges and use that as our answer. So let's begin. So slope is calculated as the difference in y divided by the difference in x. Since we're taking the centers of squares 200 and 2000, that means that if we take the distance vertically between the centers of these two squares, even though we know that 2000 lies in the bottom row and 200 lies in the top row, the distance between these two vertically will not be m, because at each end there'll be 1/2 left out, because we're just connecting the centers. So the difference vertically would be m minus 1. As for the difference horizontally, well, we can take 200 as 200 mod n, because 0 is a multiple of all numbers. So since we know that 0 is a multiple of n and 200 is less than n, 200 is just kind of like the residue left over when 0 is divided by n. So this value would be 200 mod n. If we look at the bottom row, since the bottom row's x position would just be 2000 mod n, since we're just going to keep on dividing n's from it, and whatever is left is going to be the x of this, we can express this as 2000 mod n. So the x position on the lowest row would be 2000 mod n, and the x position on the uppermost row would be 200 mod n. So that means the difference in the x positions with respect to these 2 points would be 2000 mod n minus 200 mod n, which would give us 1800 mod n. And we know that this slope cannot have a value of 1 or -1. So it cannot have a value of plus minus 1. In order to simplify this into a usable term, we would take the reciprocal, which in this case would be 1800 mod n divided by m minus 1. And this is not equal to plus minus 1. So by multiplying across, we would get 1800 mod n can't be plus minus m minus 1. Now, here we can test out all the cases to find out which ones don't work. And we can do that by plugging in the values of m we've already found, 3, 5, 7, 9, to see which of them breaks these rules, which values of n breaks these rules. So we got to start with the first case, m is equal to 3. Doing that, we see that 1800 mod n can't be plus or minus 3 minus 1, which is 2. Now, this further means that by adding or subtracting 2, 1798 or 1802 can't be perfect 0 mod n. So then any numbers that make this 0 mod n in this range between 667 to 999 would not work in this case, because they would give us a perfect 1 or -1. We see that this only works for values 899 and 901. both odd numbers in the range between 667 and 999. So from this range, we just need to take all the odd numbers and subtract it from 2. So just by using some simple counting abilities, we find out that the number of odd numbers in this range is 167. But since we have to subtract them from 2 because we can't take numbers that give us 0 mod n when taking 1798 and 1802, we subtract cases 899 and 901 from this. So we subtract 2 cases, which give us a grand total of 165 working values from the first case. Now on to the second case. If we plug in 5 into this equation, we see that 1800 mod n cannot equal to plus minus 5 minus 1, or 4. And then if we take this 4 to the other side by adding or subtracting it, we get that either 1796, which is plus 4 minus 4 on this side, or 1804 cannot give us 0 when taken mod n. That means that odd numbers in range of 401 to 499 cannot be factors of 1796 and 1804. Unfortunately, once again, we see that 449 and 451 are both factors of this number that are odd and lie in this range. So to take account for their cases, we just need to find out the total number of odd numbers and subtract 2 for both of these cases that don't work. So typically there would be 50 different odd numbers between 401 to 499. But since we see that cases 449 and 451 work because then they would force this inequality to be true, we have to subtract 2 from this case, giving us a total set of 48 working cases in this range. Next, we do the same thing with 7. If we plug in 7 into this equation, we get that 1800 mod n cannot be equivalent to plus minus 7 minus 1, which is 6. So if we once again subtract 6 and add 6, we see that n cannot be a factor of 1806 or 1794. Once again, if we do the math, we see that in this range from 287 to 333, there lies 2 factors that would force this to be true. And these numbers are 299 and 301. So to find out the number of values of n in this case that would work, we would take all the odd numbers once again, because remember, at the beginning of the problem, we remember that m and n are odd numbers. We would take all these odd numbers in between and then subtract them from 2 again, because they're 2 not working cases. So typically there would be 24 odd cases. But since we found out that these 2 won't work, as they're going to force this inequality to be true, there are only 22. So finally, we test out our final case, where m is equal to 9. So if m is equal to 9, that means 1800 mod n cannot be equal to 9 minus 1, which is 8. That means that n cannot be a factor of 1792 and 1808. Now this case is slightly unusual because when we take the factors, we find that 224 and 226 end up being the factors in this range. And we would exclude these values because anyways, we're only taking odd numbers because that's what the problem is asking for. But these numbers are between slopes that won't work, so any numbers in between them would be part of slopes that don't work. 225 is a number that's in between them. And unlike these 2 numbers, it is odd. So we would normally count this. But seeing how it is in between the slopes of 2 values that won't work, we see that 225 will also not work. So whereas this case originally would have 14 odd numbers between 223 to 249, we have to subtract 1 because 225 won't belong because it's just in between two non-working values. So from the 14 we would subtract 1, giving us 13 for this final case. So now we would just need to add up all these terms. 168, 48, 22, and 13. Doing so would give us 248, which is our end answer. So just like that, we've solved number 12 from the AIME II of 2020. So this number 12 on this AIME was pretty weird. Like, out of all the AIME problems I've gone over, this was really unusual. But this problem is quite fun on its own. So I hope you enjoyed this problem and hopefully figured out and understood how to solve the number 12 from the AIME II of 2020.